Lesson 111. In this lesson, we're going to take a look at angles, okay? How we can calculate angles between two planes, angle between two lines, and angle between a line and a plane. So first off, let's consider angle between two planes. When I describe direction of planes, obviously I can use direction vectors on these planes, but you should recognize that so far, whenever we are, dealing with direction of planes, the more convenient thing to look at really is the normal of the planes, right? The vector that's perpendicular to the plane, because it's less ambiguous. So the same thing happens when we are looking for the angle between two planes. It might be the most convenient way to find angle between N1 and N2, okay? Since the two planes are given in Cartesian form, that's really convenient now because N1 would be the coefficients of x, y, z, so 1, -1, and 1. And N2 is also the coefficients of those variables, 1, 1, and 0 in this case, okay? So now angle between two vectors is cosine theta, right? Using that dot product relation. So N1 dot N2 over magnitude of N1 times magnitude of N2. You may want to put the absolute sign here just to make sure we're talking about the acute angle between the two vectors, okay? So what does that give us? 1 times 1 minus 1 times 1, -1 times 1, but that's what I mean. So root 3 for the first one, root 2 for the second one. This is 0. This is like the easiest thing that we can ask for because our cos of 0 is 90 degrees, meaning that the two planes that are given are perpendicular to each other, okay? Secondly, let's look at angle between two lines. Well, angle between two lines, angle between two vectors on the line, right? So the most convenient thing to use, of course, would be direction vectors. So find the angle between the direction vectors. Okay. Since the two lines are given to us in standard form, I can easily rearrange them into y equals to mx plus b form. So that the gradient, which is rise over run, can be turned into the direction vector. So here gradient is -2 over 1, so that means I have 1 and -2 for D1, okay? For the second line, I have 3x minus 2y equals to 8. Well, let's take a step. -2y is -3x plus 8, meaning that the line is y equals to 3 over 2x minus 4 in y equals to mx plus b form. And so D2 is 2, 3, okay? So now once again, we have two vectors. I want the acute angle between D1 and D2. Let's set up cosine theta equals to D1 dot D2 over D1 magnitude times magnitude of D2. Okay, keeping that in the first quadrant. What have we got here? I have 1 times 2, -2 times 3, minus 6. I have 1, 4, square root. The other one's 4, 9, square root. This gives me the ratio of 4 over root 5 and multiplied by root 13. Finding the inverse cosine of this. Using my calculator, I get 60.3 degrees. Okay. Last but not least, what if I'm interested in finding the angle between a plane and a line? All right. So line, we like the direction vectors. Planes, we prefer the normal. But the angle between the plane and the line must be the angle between the direction vectors of the two. So, but we can think about a relationship, right? So D1 in this diagram is the direction vector of the line. It makes an angle X with the normal of the plane, and then makes an angle Y with the direction vector, D2, on the plane. So it looks like what we can do is we can make use of a complementary angle relationship to find the actual direction or angle Y that we need, okay? So let's, do it in a logical way first, which is to find the angle between the normal and the direction vector, and then take the complement. All right. So looking at the given in example 3, okay, the line is given in parametric form. I can identify its direction vector using the coefficients of t, the parameter, so -1, 2, and 6. And the plane is given in Cartesian form again, music to our ears, because then its normal is 2, -1, and 3. Okay, so let's find the angle between direction vector of the line and the normal. So cos theta is d1 dot n1, d1 and 1 magnitude multiplied together. Okay, so this is -2, 6 times 3 is 18. D1's 1, 4, 36 square root. Magnitude of n1, 4, 1, 9. Okay, what do we have? We have 18 minus 4, 14. In the denominator, 36, 4, 40, 41, and then 10, 14. Okay, so this is cosine theta. Taking our cos of theta, of this ratio, I get 54.2 degrees, rounded to 3 significant figures. But I know this is not it, right? So this is only the complementary angle. So the angle between the line and the plane is 90 minus 54.2, which is 35.7. Okay, all right. So once again, this is in 3 suffix. Now, one thing that I want you to note is that, remember there was this trig identity, right? So sine x is actually equal to cosine of 90 minus x. So if you remembered this trig identity, we can, adjust our calculation for the angle so that to find the angle between a plane and a line, we could consider using sine theta equals to d1 dot n1 over d1 magnitude times n1 magnitude as well, right? And this way we can find the angle directly, okay? Okay, so that's all from lesson 111.